Hi, here we are discussing about a project, a VLSI Architecture for Myocardial Infarction Stages Classifier for Wearable Healthcare Applications. Here, the myocardial infarctions is a serious cardiac problem that kills millions of people globally each year. So, myocardial process in various stages depending on its severity and generating significant alterations in the electrocardiogram signal. Capturing these fluctuations is a critical and requiring continual monitoring of the patient ECG signals. As a result, developing a low-power VLSI designs is critical for addressing the myocardial protections. This paper offers a totally innovative hardware solutions for pre-processing based on field programmable gate array. The proposed detection systems is built on the basics of myocardial feature extractions. However, the detection phases employs an innovative, straightforward and effective technique. The center derivative feature extractions and intermediate value theorems are used to develop the innovative approach for determining the Q peak, R peak, T peak and S peak from the ECG signal. The proposed structures was implemented on FPGA using Wearable HDLs and synthesized using Vertex 5 FPGA. The proposed systems dependently execution times and anticipated FPGA resources were compared to those obtained with the standard deviations technique to determine its effectiveness. The dataset from the MIT BIH arrhythmia database were utilized to validate the proposed design. Finally, the comparisons was done with the area, delay and power evaluations. Okay, now we can verify the base purpose. So this base purpose is full and fully designed for the ECG classifications which using a myocardial infarctions. Okay, so here as per the architectures in figure 1, the proposed architectures of this paper, ECG delineations and MI classifications, we have remodified it. This is the existing architectures in here. Okay, so here what are the functionality they are developed means here they are developed with the ECG feature delineations. Okay, and inside of this ECG feature delineations point they have used bandpass filters, differentiators and QRS peak detections and ECG RAM. Okay, and additionally they will called as T-wave delineations and P-wave delineations and some counters with ISO line and MI feature extractions. Okay, we have improved this architectures and additionally the feature extractions process we are remodified with a pre-processing stage with the same bandpass filter. Okay, so here this is a proposed architectures we have used in this paper. So here this is a ECG signal input. It will be started with bandpass filter, derivative filter, squaring, integrator filter, low pass filters. It's the total module. It's called as a pre-processing stage. After this pre-processing stage we are come with MI feature extractions and R wave delineations. Okay, so this R wave delineations we are finding the maximum and minimum R peak level with the R peak boundaries. Okay, after that we are calculated the heart rate calculations. Okay, and we are using this R peak and it will be given to the MI feature extractions. We are finding the T peak, Q peak and ST segmentations and the QRS width. Okay, so this MI feature extractions we are given into the decision logic and we are finding the accurate predictions and early predictions and normal and abnormal values. Okay, and this work we have developed in Wearable HDL. So this is a Wearable HDL code we have developed it. Okay, so this is a myocardial infarctions input and outputs. Okay, you can verify it here. This is a top model architecture. Okay, here we are given an input from the ECG modulations code with using a MIT BIH database. Okay, so here we have used 3 number of files, 2 normal and 1 abnormal files to map with here this project. Okay, so here we are taken an output. First one is a heart rate and second one is a TP, true positive, false negative, false positive. Okay, and the output from the decision logic it will come up with the normal, abnormal, early predictions and accurate predictions. Okay, and this work start up with FIR filter. So this FIR filter output given to derivative filter, squaring, integrated filters, R wave delineations point, and we are finding here for R peak and R peak enable. Okay, and this is a heart rate calculations. Okay, so after this modules we have used the same integrated data, and this MI feature extractions we have developed for R peak value, T peak, Q peak, S peak, P peak, ST segment, and QRS width. After that we have come up with a decision logic. Okay, it will be come up with the final output. Okay, and this simulation process we have done on modelism. Okay, so this is a simulation technique for this ECG signal. Okay, so here this is a normal signal and this is a heart rate. Okay, so as per the signals you can analyze the heart rate values. Okay, and prediction, the normal, abnormal, early predictions and accurate predictions. Okay, so you can analyze it. Okay, and this is a filter output and derivative filter, squaring, integrated filter, R peak delineations, heart rate calculations, MI feature extractions. Okay, and normal, abnormal decision logic. Okay, okay, so here you can analyze all the thing. The mostly normal will access in high. Okay, and we can possible to give another set, so that is abnormal cases. Okay, so here up to this time period the normal ECG signals was occur. Okay, so in sometimes it will predict with abnormal cases. Okay, as per the heart rate increases. Okay, example, heart rate goes high means at the time it will be predict the abnormal cases, and time period, after this time period it will be started the completely abnormal. At the time the earlier predictions will predict some glitches, and after it will be provide pulses, and after that it will start up with the accurate predictions. Okay, so on the time you can analyze the prediction stages. Okay, and you can analyze the normal and abnormal ECG forms. Okay, with all the outputs, band pass filter output, derivative output, square data, integrated data. Okay, derivative. Okay, so everything you can analyze it, heart rate calculations. Okay, and here the heart rate calculations also mismatch with the higher value. Okay, that's it. Okay, and here this work we have synthesized with the Xilinx Vertex 5 FPGA. Here you can analyze with the number of slice registers, number of LUTs, occupied slices, IOB, and it will be take a very minimum utilizations. It's occupied only 8% compared to other works. Okay, so here the LUT will take 2505 numbers only. Okay, and synthesis report you can analyze delay. Okay, delay will occupied only minimum 5.250 nanoseconds. Okay, and you can analyze the RTL schematic here. Okay, so FIR filter. Okay, so FIR filter, derivative filter, squaring, integrated filter, R wave delineation, heart rate calculations, MI feature extractions, and normal, abnormal decision logic. Okay, and we have analyzed power consumptions here. Okay, so power will take a 591 millivolt. Okay, and we have written an abstract document for this project. So base paper abstract, improvement of this project, proposed title, proposed abstract, block diagram, disadvantages, advantages, and related notes with VLSI. Finally come up with the literature survey and references. Okay, thank you.